In 2021, an observatory in China detected a gamma-ray signal from inside our galaxy, so powerful it broke records. So scientists did what they always do. They pointed every telescope they had at the exact location to find out what was producing it. Every single wavelength came back completely silent. The only thing screaming from that spot in the sky was the gamma rays themselves. No pulsar, no black hole, no supernova remnant, no object of any kind. 5 years later, and study after study, nobody can tell you what is producing one of the most violent signals in our galaxy. If that sentence made you do a double take, good. Because it made the entire astrophysics community do the same thing for 5 straight years. If you are new here, welcome. Subscribe, get comfortable, and stay until the end. Because by the time this is over, the silence around that signal is going to feel a lot louder than it does right now. Now, let's get into it. Part 1. The invisible explosion. There is something in our galaxy that should not exist. Not in the way that scientists say that when they're being dramatic. Not in the way a headline uses it to pull you in before explaining that actually, it fits neatly into existing models once you read the fine print. This is the other kind. The kind where 5 years of looking with every instrument humanity has ever pointed at the sky comes back with the same result, over and over again. Nothing. A source producing the most powerful radiation ever recorded from within the Milky Way, and not a single telescope in the world can find what's making it. Let that settle for a second. We're not talking about something happening in a distant galaxy billions of light years away, so remote that the signal barely reaches us, and we can forgive ourselves for not understanding it. We're talking about something inside our own galaxy, our home, a place we have been studying since Galileo first tilted a lens toward the sky in 1609. And right now, buried somewhere in the gas clouds of the Milky Way, something is accelerating particles to energies so extreme that the machines we built, the most powerful particle accelerators in human history, cannot come close to replicating them. 100 times beyond what the Large Hadron Collider can produce. 100 times, and we cannot find it. The object has a name. Scientists call it LHAASO J2108+5157. That string of letters and numbers is what happens when you detect something before you understand it. You catalogue it, you give it coordinates, you file it, and you start investigating. The LHAASO designation tells you it was found by a specific observatory in China. The coordinates tell you where in the sky it sits, but the name tells you nothing about what it is, because as of 2026 nobody knows. The first detection happened in 2021. A team operating the large high-altitude air shower observatory in the mountains of Sichuan province noticed something coming from a patch of sky that had no business producing what it was producing. Gamma rays. Not just gamma rays, but ultra-high energy gamma rays at the peta-electron volt scale. A peta-electron volt is a unit of energy so large that we rarely encounter anything in nature capable of generating it. 1 peta-electron volt is 1 quadrillion electron volts. For comparison, the protons accelerated inside the Large Hadron Collider at CERN, the machine that took decades to build, spans a ring 27 kilometers in circumference and consumes enough electricity to power a small city. Those protons reach energies of around 14 tera-electron volts at their peak. 14 trillion electron volts. That sounds enormous. And then you realize that LHAASO J2108+5157 is producing gamma rays at 1 peta-electron volt. That is roughly 70 times more energetic than what CERN achieves in a machine that occupies a point of space somewhere in our own galaxy, and that we cannot see with any instrument we possess. The gamma rays themselves are not the direct emission from the accelerator. This is a critical distinction, and it is one of the first things that makes this mystery so layered. What LHAASO is detecting is the secondary product of a process. Something in that region of the galaxy is taking particles, protons most likely, and hurling them to peta-electron volt energies. Those protons then slam into the gas and dust clouds surrounding the source, and when they collide with the nuclei of atoms in the gas, they produce gamma rays as a byproduct. So what we are seeing is the aftermath. We are seeing the shockwave from an explosion we cannot locate. We are reading the fingerprints of a machine we cannot find. The gamma ray signal is real. Multiple instruments have confirmed it. It is structured, localized, persistent, and far too intense and organized to be written off as background noise or a statistical artifact. Something is there, but the something itself is dark. Completely, thoroughly, stubbornly dark. Scientists have a term for this. They call it a dark emitter, and they do not mean that metaphorically. They mean it in the most literal observational sense possible. The object emits no detectable radio waves. It produces no X-ray signature. It shows no infrared glow. It appears at no optical wavelength. In every part of the electromagnetic spectrum that our telescopes are tuned to detect, the region surrounding this gamma ray source is empty, quiet, featureless. It is as if someone switched off a star and left only its gravitational influence behind. Except here what remains is not gravity pulling on nearby matter, but raw, overwhelming energy pouring through gamma rays from a machine that casts no shadow, generates no glow, and leaves no trace of its own existence except in the particles it flings outward. The scale of what we do not understand here is the terrifying part. This is not a gap in knowledge at the frontier of the observable universe, where we can excuse ourselves by saying the distance is too great or the signal too faint. This is happening in our own galaxy, in our own backyard by cosmic standards, and the mystery is not fading with time. Over the next 5 years, scientists tried everything. They turned the best instruments in the world toward this object. They ran follow-up studies with radio arrays, infrared observatories, X-ray space telescopes, and optical cameras capable of imaging objects billions of times fainter than anything the naked eye could detect. And every single attempt made the mystery worse. We are detecting effects without a visible cause, and in the history of modern astronomy, that is one of the most unsettling sentences you can write. Part 2. The most powerful signal in the galaxy. To understand why the scientific community reacted to LHAASO J2108+5157 the way it did, why the detection prompted urgent follow-up campaigns across multiple continents, why researchers who normally work in separate subfields began coordinating observations within months of the catalogue publication, why the source has remained a focal point of high-energy astrophysics for 5 years, and counting. You need to understand what a pevotron is, and why finding one, even a hidden one, even one that resists every attempt at identification, matters enormously to a field that has been wrestling with a particular fundamental question for over a century. A pevotron is the name astronomers give to any astrophysical object capable of accelerating particles to peta-electron volt energies. The term is a portmanteau, a compression of peta-electron volt and accelerator, and it was coined because the category needed a name before the objects populating it were clearly identified. That sequencing, naming a category before its members are confirmed, reflects something important about the state of the field. Physicists knew pevotrons had to exist long before they could point to one with confidence. The reason they knew this takes us back over a century, to the discovery of cosmic rays themselves. Cosmic rays are high-energy particles, primarily protons and atomic nuclei, with a smaller component of electrons that travel through space at velocities close to the speed of light and rain, down continuously on Earth's atmosphere. They were first identified in the early 20th century through experiments showing that the ionization of air increased with altitude rather than decreasing, as would be expected if the ionizing radiation came from radioactive materials in the ground. The Austrian physicist Victor Hess made the critical balloon-based measurements in 1912 that demonstrated the radiation was coming from above, from space, and he received the Nobel Prize for the discovery in 1936. Since then, physicists have been measuring cosmic rays at ground-based observatories, at high-altitude balloons, and eventually in space, characterizing their energy spectrum, their composition, and their arrival directions with increasing precision over more than 100 years of effort. And for essentially that entire century, the central question has remained stubbornly open. Where do cosmic rays come from? What produces them? What accelerates protons and nuclei to the extraordinary energies observed, energies that, at the high end of the spectrum, exceed anything produced in the most powerful particle accelerators ever built by factors of millions? The question matters not just as a matter of scientific curiosity, but because cosmic rays are a significant component of the energy budget of the galaxy. They exert pressure on the interstellar medium, they ionize molecular cloud material and influence the chemistry of star formation. They contribute to the heating of the galactic gas. Understanding their origin means understanding a fundamental aspect of how the Milky Way works as a physical system. For most of the 20th century, the leading answer was supernova remnants. The argument was compelling and well developed. When a massive star explodes, it releases a shock wave that expands outward into the surrounding interstellar medium at thousands of kilometers per second. At the boundary of that shock wave, a process called diffusive shock acceleration operates. Charged particles, protons, atomic nuclei, become trapped in the turbulent magnetic field near the shock front and bounce back and forth across it repeatedly, gaining a small increment of energy with each crossing. Over thousands of years, as the remnant expands and the shock decelerates, particles accelerated through this process accumulate to high energies. They eventually escape the remnant and propagate into the broader interstellar medium as cosmic rays. The energy budget works out reasonably well. The kinetic energy released by galactic supernova explosions, if a few % of it goes into cosmic ray acceleration, is roughly sufficient to maintain the observed cosmic ray flux against losses and escape from the galaxy. The mechanism is physically well understood. The energy source is abundant. The model is elegant. But here is where the problem begins, and it is a problem that has been nagging at the field for decades. Supernova remnants, despite being the leading candidate for over half a century, have struggled to produce convincing observational evidence that they can accelerate particles all the way to peta-electron-volt energies. The theoretical ceiling for diffusive shock acceleration in a supernova remnant is in the right neighbourhood. Models suggest the process can, in principle, reach somewhere around the peta-electron-volt scale during the early, most energetic phase of a remnant's expansion. But the observational evidence for actual peta-electron-volt acceleration in known supernova remnants has been incomplete and contested. The gamma-ray signatures expected from peta-electron-volt protons interacting with surrounding gas have either been absent, ambiguous, or explicable through alternative mechanisms involving lower-energy electrons rather than high-energy protons. The crown that supernova remnants were assumed to wear, the title of primary galactic pevatron, had never been firmly placed on any specific object's head, so astronomers broadened the search. Pulsar wind nebulae were explored as candidates. Stellar wind bubbles around massive star clusters were considered. The regions near the galactic centre, with their dense gas and strong magnetic fields, attracted attention. And then LHAASO came online in the mountains of Sichuan province and began its survey of the gamma-ray sky with a sensitivity and energy reach that no previous instrument could match. When the collaboration published their first major source catalogue in 2021, the sources it contained were not marginal detections at uncertain energies. They were clear, statistically robust signals at energies definitively above the peta-electron-volt threshold. Whatever was producing those signals, whatever physical objects or processes were responsible, they were operating as pevatrons in the most literal and unambiguous sense. The century-long search for confirmed galactic pevatrons had, suddenly, a set of candidates. LHAASO J2108+5157 was among them, and it was different from the others in a way that made it uniquely important and uniquely frustrating. Because whatever LHAASO J2108+5157 is, It is undeniably operating at or above the peta-electron volt threshold. The gamma-ray signal confirms this beyond reasonable statistical doubt, and yet it has no visible counterpart. No object that can be identified as the source. We have found the output of a pivatron without finding the pivatron itself, and that distinction is not a minor technical detail. It is the entire problem. This is worth pausing on, because the chain of events between the source and the detection is longer and more indirect than it might initially seem. The gamma rays that LHAASO detects are not the primary emission of whatever object is driving this signal. They are a consequence, several steps removed from the source itself. The actual machine, whatever it is, wherever it sits within the positional uncertainty region of the gamma ray emission, takes particles, accelerates them to peta-electron volt energies, and releases them into the surrounding medium. Those accelerated particles, primarily protons, travel outward from the source and eventually encounter the dense molecular clouds in the region. When a peta-electron volt proton ploughs into the nucleus of a hydrogen or helium atom in the cloud, the collision is energetic enough to produce new particles, specifically neutral pions, which are unstable and decay almost immediately, with a lifetime of roughly 84 attoseconds, into pairs of gamma-ray photons. Those photons travel at the speed of light across thousands of light years and eventually reach Earth, where they enter the atmosphere and initiate the particle showers that LHAASO's detectors reconstruct. Source accelerates particles. Particles travel through cloud. Cloud produces gamma rays. Gamma rays travel to Earth. Earth detects gamma rays. And at no point in that entire chain does any instrument directly observe the source. The molecular clouds play a dual role in this story that is worth understanding clearly. They are on one hand the reason the source is detectable at all. Without dense cloud material for the accelerated protons to collide with, the protons would disperse freely into the lower density interstellar medium. The collision rate would drop dramatically, and the secondary gamma-ray production would fall below detectable levels. If this pivatron were sitting in an empty region of the galaxy with no nearby gas targets, the protons it produces would simply spread outward invisibly, and we would never know the source existed. The clouds are the medium that converts the source's invisible output into a detectable signal. They are, in the most literal sense, the only reason this object is on any astronomer's radar. But the clouds are also a complication, and the complication is fundamental. Their presence immediately raises the question of whether they are hiding something. If the source is embedded within the molecular cloud complex, physically located inside the column of dense gas and dust that makes up the cloud, then the same material that makes the gamma-ray signal detectable might also be absorbing or scattering the electromagnetic radiation from the source at other wavelengths. The clouds could be acting simultaneously as a detection mechanism and as an obscuring screen. The question is whether the electromagnetic silence at all other wavelengths is a consequence of that obscuration, or whether it reflects a genuine absence of emission from the source itself. 5 years of targeted searches, including an infrared study specifically designed to penetrate the dust that blocks other wavelengths, have not resolved that question in the direction of obscuration. The searches have instead progressively eliminated the obscuration hypothesis and pushed the investigation toward the more uncomfortable alternative. But the question itself, hidden by the clouds, or genuinely dark, is the question that has driven this investigation from the beginning. Because the answer determines whether this is a known type of object in an unusual environment, or something that has no category in the existing literature. We are seeing, with confidence, the most powerful particle accelerator in the galaxy. We cannot see it directly. We can only see what it does to the material around it. And what it does to the material around it, the gamma-ray signal, real and confirmed and persistent across 5 years of observation, is the entirety of what we know about it. Everything else is the absence of evidence, and in this case that absence is not nothing. It is the shape of a mystery that the field is only beginning to know how to approach. Part 3. How we found it, and why that matters. the instrument that found LHAASO J2108+5157 is not a telescope in any conventional sense. When most people hear the word telescope, they picture something with lenses or mirrors, something that gathers light and focuses it, something you could in principle point at the sky and look through. The Large High-Altitude Air Shower Observatory is none of those things. It does not collect light. It does not focus electromagnetic radiation onto a sensor array. It does not take pictures of the sky the way Hubble does, or detect X-ray photons the way Chandra does. It does not even look up in any meaningful sense. What LHAASO does is something stranger and more indirect than any of that. It detects the consequences of the sky reaching down and touching the atmosphere. To understand why that distinction matters, you need to think about what happens when an ultra-high energy gamma ray from somewhere in the galaxy actually arrives at Earth. The intuitive picture, a particle travelling across the galaxy and landing in a detector, is not what occurs. The atmosphere intervenes. A gamma ray entering the upper atmosphere at peta-electron volt energies carries so much energy that the moment it encounters a nucleus in the air above, it triggers a cascade of secondary particles. The original gamma ray is gone, converted in that first collision into a spray of electrons, positrons, additional photons, and muons. Those secondary particles carry forward the energy and direction of the original gamma ray, but now they are many particles instead of one, spreading outward in a broadening cone as they travel downward through the atmosphere. As those particles travel, they collide with more atmospheric nuclei, producing more secondaries, which produce more secondaries still, each generation of particles slightly lower in energy than the last, the cone widening continuously as the shower descends. By the time this particle cascade reaches ground level, it has spread across hundreds of square meters, sometimes more, a thin disk of energetic particles racing downward at nearly the speed of light, carrying within its geometry the encoded information about where the original gamma ray came from and how much energy it had. LHAASO is the instrument built to read that encoding. The facility covers over 1 square kilometre of ground in the mountains of Sichuan province in China, at an altitude of around 4,300 metres. That altitude is deliberate. Higher elevation means less atmosphere above the detectors, which means the particle shower arrives with more of its structure intact, less degraded by additional scattering during the final kilometres of descent. The site is instrumented with 2 primary detector systems working in concert. The first is a large array of water Cherenkov detectors, enclosed pools of ultra-pure water in which charged particles from the shower produce faint flashes of blue Cherenkov light as they travel faster through the water than light itself can travel through that medium. Those flashes are recorded by photomultiplier tubes, devices sensitive enough to register individual photons. The second system consists of muon detectors buried underground, designed specifically to catch the muon component of the shower, which carries different information than the electromagnetic component and helps scientists distinguish gamma-ray-initiated showers from the much more common showers initiated by cosmic ray protons, which are a background that must be identified and removed from the data. The key insight behind the entire facility is this: by measuring the precise arrival time, the spatial density, and the distribution of particles landing at multiple detector stations simultaneously, scientists can reconstruct the direction the original gamma ray came from with considerable accuracy, and estimate its energy from the total number and energetics of the secondary particles they catch. You're not observing the source directly. You're reading the imprint the source left in the atmosphere and then in the detectors. It is genuinely like reconstructing what caused an explosion by analysing the pattern of shrapnel that spread outward from it. You can work backward from the debris to infer properties of the original event, but the precision of your reconstruction depends entirely on how well you understand the debris, how many pieces you catch, and how accurately you can account for all the ways the shower might have spread and shifted as it travelled through miles of atmosphere before it reached you. What makes LHAASO remarkable is how extraordinarily good it is at exactly this reconstruction. It is among the most sensitive ground-based gamma-ray detection facilities ever built, capable of recording events at energies that no previous instrument could reach with the same statistical confidence. Earlier generations of air shower arrays, built at lower altitudes or covering smaller areas, struggled to accumulate enough shower events at the highest energies to make statistically meaningful statements. LHAASO changed that. Its combination of large collecting area, high altitude, and the two complementary detector systems gives it a combination of sensitivity and background rejection that represents a genuine step forward in the field. When the LHAASO collaboration published their first major source catalogue in 2021, the community understood immediately that these detections were not weak, marginal signals sitting at the edge of statistical significance, where you might worry that a slightly different analysis would make them disappear. These were real. The numbers were compelling, the signal to noise was robust, and the source positions were determined well enough to make follow-up observations meaningful. Follow-up observation was not just warranted, it was urgent. And here is where the story takes the turn that makes LHAASO J2108+5157 so frustrating and so fascinating. Even with all that sensitivity, even with all that engineering and altitude and detector sophistication, LHAASO cannot pinpoint the origin of a gamma-ray signal with the same precision that an optical telescope can pin the position of a star. This is a fundamental limitation of the air shower technique, not a flaw in the instrument's design. When you're reconstructing a direction from the geometry of a particle shower, you're working with a statistical reconstruction. You're fitting a model to a pattern of detector hits and asking what incoming direction best explains the pattern. The precision of that fit is limited by shower-to-shower fluctuations, by uncertainties in the atmospheric models you use, and by the finite spacing of your detector array. For LHAASO, the angular resolution at the relevant energies is measured in fractions of a degree, typically somewhere between 1/10 and 1/2 of a degree depending on the energy range and the analysis method. A fraction of a degree sounds precise, and in absolute terms it is genuinely impressive for a ground-based instrument. But here is the problem that fraction of a degree creates in practice. The distance to LHAASO J2108+5157 is estimated at roughly 10,000 light-years. At that distance, 1/10 of a degree corresponds to a physical region of space approximately 170 light-years across. Half a degree corresponds to a region over 800 light-years wide. So when LHAASO says it has detected a source at a particular position in the sky, what it is actually telling you is that the source lies somewhere within a circle on the sky that, at the distance of this object, encompasses a region of space that could comfortably contain thousands of individual stars and all the interstellar material between them. That is not a pinpoint. That is a search area. Follow-up observations with other telescopes were designed to work within that search area and find the specific object responsible for the gamma-ray emission. The strategy was sound. Point radio telescopes, X-ray satellites, infrared facilities, and optical cameras at the region LHAASO identified. Look for any object within that area that has the kinds of properties associated with extreme particle acceleration. A pulsar, a supernova remnant, a compact binary system, a star-forming region with unusual energetics, anything that could plausibly be driving gamma-ray emission at peta-electron volt energies. The logic was that even if the source itself were not immediately obvious, the combination of the LHAASO position constraint and follow-up detections at other wavelengths would narrow the candidate list down to 1 or 2 objects, and from there the identification would follow. That is not what happened. The follow-up observations came back empty. Not marginally empty, not ambiguously empty, but thoroughly, redundantly, multiply confirmed empty. Radio searches found no counterpart. X-ray observations found no compact source. Infrared surveys found no heated dust, no shocked gas, no extended nebula structures. optical searches found nothing. The region that LHAASO's best reconstruction pointed to was, across every wavelength that astronomy knows how to use, completely featureless. The most advanced detection system ever built for high-energy gamma-ray astronomy found a signal of undeniable importance, a source producing radiation at energies that stagger the imagination, operating in our own galaxy, leaving an unmistakable mark in the particle showers raining down on a square kilometre of Chinese mountain. And then every other tool humanity has for looking at the sky confirmed, independently and repeatedly, that there is nothing in that region to find. LHAASO did its job perfectly. It found the signal. It characterized the energy. It provided coordinates good enough to search. The problem is not the instrument. The problem is what the instrument found, or rather, what it found the absence of. A source that is real beyond any reasonable statistical doubt, located somewhere in a defined region of our galaxy, producing the most energetic gamma rays ever recorded from a galactic object, and invisible to every other form of observation we possess. That gap between what LHAASO detected and what everything else could confirm is the gap this investigation has been trying to close for 5 years. It has not closed. Part 4. Turning every telescope toward it. When an object this energetic shows up in a gamma-ray survey, the standard protocol in astrophysics is rapid multi-wavelength follow-up. You do not wait. You do not sit on the detection and schedule observations for next year's telescope time allocation cycle. You coordinate, you communicate, and you move. Within months of the 2021 LHAASO catalogue publication, teams around the world had begun pointing radio telescopes, X-ray satellites, infrared observatories, and optical cameras at the region of sky containing LHAASO J2108+5157. The expectation was not that they would immediately solve the mystery, not that the first observation would return a clean identification and close the case. The expectation was simply that at least one of those observations would return a candidate. Something to anchor the investigation, a compact source, an extended nebula, a star cluster with unusual properties, any object at all that could plausibly be driving gamma-ray emission at peta-electron-volt energies. Give us something to work with, give us a direction. The expectation was wrong. Start with radio, because radio is where you would reasonably expect to find the first clue. Radio telescopes are extraordinarily sensitive instruments, and they are specifically tuned to detect the kinds of emissions that high-energy astrophysical sources almost always produce as a matter of basic physics. Pulsars, rapidly rotating neutron stars that sweep beams of radio waves across space like cosmic lighthouses, are among the brightest radio objects in the galaxy relative to their physical size. They show up in surveys with unmistakable signatures, sharp, periodic pulses arriving with clockwork regularity, their timing so precise that astronomers use them as natural clocks to test theories of gravity. If a pulsar were responsible for the gamma-ray emission in this region, the radio surveys would have found it. Relativistic jets from compact binary systems, where a black hole or neutron star accretes material from a companion star, produce synchrotron radiation as the jet material accelerates and spirals in magnetic fields. That synchrotron emission is bright in radio. Supernova remnants produce extended radio shells as electrons in the remnant's magnetic field radiate. Star-forming regions produce radio emission from ionized gas heated by young, massive stars. The range of astrophysical objects and processes that produce radio emission is enormous, and the sensitivity of modern radio facilities is such that finding the radio counterpart of a known gamma-ray source is, under normal circumstances, one of the more straightforward tasks in observational astronomy. These were not normal circumstances. The radio searches of the LHAASO J2108+5157 region returned nothing. No point source at the expected position. No extended structure consistent with a supernova remnant or a pulsar wind nebula. No periodic pulsations that would identify a neutron star. No jet-like morphology. Nothing that could be unambiguously placed within the positional uncertainty region of the gamma-ray source and identified as its origin. The radio sky in that direction was, by every meaningful measure, quiet. Move to X-rays, because if radio failed, X-ray astronomy is the next natural place to look for the engine behind a peta-electron-volt gamma-ray source. X-ray astronomy is the discipline built specifically for studying the most energetic, most violent environments in the universe. Black holes accreting mass from companion stars are luminous X-ray sources. The accretion disk heats to temperatures of tens of millions of degrees and radiates intensely in the X-ray band, making these systems some of the brightest objects in the X-ray sky. Pulsars emit X-rays from their hot surfaces and from the shock regions where their winds interact with surrounding material. The expanding shock waves from supernova remnants heat interstellar gas to temperatures that produce diffuse X-ray glow spread across portions of the sky large enough to see clearly with space-based observatories. When the Chandra X-ray Observatory launched in 1999, it transformed the field by producing X-ray images with angular resolution approaching that of optical telescopes, revealing structures and point sources that previous X-ray missions could only detect as blurs. If there is a compact high-energy object in the LHAASO region, a neutron star, a black hole binary, anything involving accretion or extreme magnetic fields, Chandra or its equivalents should have the sensitivity to find it. X-ray searches of the region came back empty. No compact point source at the expected position. No diffuse emission consistent with a hot shock wave expanding into the surrounding medium. No signatures of accretion. No spectral features associated with extreme magnetic field environments. The X-ray sky in the direction of LHAASO J2108+5157 was as blank as the radio sky, then infrared. This is where the searches started to feel genuinely strange, because infrared observations are specifically designed to see through the obstacles that block other wavelengths. The Milky Way is threaded with dust, microscopic solid particles of silicates and carbon compounds that scatter and absorb shorter wavelengths of light with remarkable efficiency. An object sitting behind even a modest column of dust will be invisible to optical telescopes. The dust simply absorbs the visible light before it reaches us. But infrared radiation, with its longer wavelengths, passes through dust far more easily. This is why astronomers routinely use infrared observations to study star-forming regions, the galactic centre, and other dusty environments where optical astronomy is essentially useless. If the gamma-ray source were embedded within the molecular clouds in this region, if it were a compact object buried inside a column of obscuring material, infrared should punch through where optical cannot. Infrared observations of the LHAASO J2108+5157 region were conducted by multiple independent teams, using different facilities and different infrared wavelength ranges. They found no heated dust structures glowing with the warmth of an embedded energetic source, no infrared nebulae, no shocked gas emission in the near or mid-infrared bands where the signatures of energetic shock waves typically appear. The region was as blank in infrared as it was in radio and in X-rays. Finally, optical. Optical telescopes represent the original and still extraordinarily powerful branch of astronomy, and modern optical facilities can detect objects of almost incomprehensible faintness. Current ground-based and space-based optical telescopes can image stars billions of times dimmer than the threshold of the naked eye, and can detect galaxies at distances where the light reaching us departed before the Earth existed. A compact object within our own galaxy, even a faint one, even one partially obscured by intervening dust, should, under most circumstances, be detectable by modern optical facilities if it has any optical emission at all. Optical searches of the LHAASO region found nothing that could be associated with the gamma-ray source. No stellar object with anomalous colours or brightness, no extended optical nebulosity, nothing. 4 wavelength regimes, 4 independent sets of observations, multiple teams, multiple facilities, multiple approaches, and the answer, uniformly across all of them, was the same single word: nothing. This is the point where you have to stop and genuinely appreciate how abnormal this outcome is, because it is easy to read a list of failed searches and come away with the impression that the source is simply faint or distant or mildly obscured. That is not what is happening here. In the catalogue of known high-energy astrophysical sources, the full population of gamma-ray emitters that astronomers have identified and studied over decades of observation, multi-wavelength darkness is not normal. It is not a common edge case. It is not something that happens with unusual or extreme objects of known types. Essentially, every gamma-ray source that astronomers have ever identified has a counterpart somewhere in the electromagnetic spectrum. Pulsars glow in radio and X-rays. Supernova remnants shine in radio, X-rays, and sometimes optical. Black hole binaries blaze in X-rays. Active galactic nuclei emit across the entire spectrum from radio to gamma rays. Stellar wind nebulae and star-forming regions leave signatures in infrared and radio. The physical processes that produce gamma rays, shockwave acceleration, magnetic reconnection, accretion, pulsar wind injection, almost invariably also produce electromagnetic radiation in other bands as unavoidable byproducts of the same underlying physics. Energy does not flow entirely into one channel, it leaks. The absence of any such leakage from LHAASO J2108+5157 is not a minor anomaly to be footnoted and moved past. It is a fundamental statement about the nature of the source. Either the object is hiding its emission through some mechanism we do not currently understand, some process of absorption or confinement that blocks all wavelengths simultaneously except for the secondary gamma rays, which cannot be blocked because they are produced externally in the surrounding cloud material rather than at the source itself, or the source is genuinely producing no electromagnetic emission of its own to hide in the first place. Both possibilities are, in different ways, deeply uncomfortable for existing astrophysical models. The teams conducting these searches were not doing shallow cursory scans of a wide region and hoping something would jump out. These were deep, targeted, carefully planned observations aimed at a specific patch of sky, with instruments operating at or near their sensitivity limits. Multiple independent groups, working with different telescopes on different continents and in different orbits, all aimed at the same coordinates, all applying rigorous analysis to their data, all coming back with the same result. The silence was not ambiguous. It was not inconclusive. It was thorough. There is a phrase that began circulating quietly in the technical literature after these results accumulated. Scientists started describing the region as an observational void, not as a metaphor, not as an expression of frustration, but as a precise technical term for a region that had been observed deeply across the accessible electromagnetic spectrum and found to be genuinely empty of detectable sources, except for the one signal that defied explanation. For the researchers involved, that silence carried a particular quality. You build a campaign like this expecting confirmation, not absence. You have the energy signal, you have the coordinates, you have the resources and the instruments and the follow-up time. You expect to find something. When you find nothing, the nothing feels different than it would if you had never expected to find anything at all. The silence was not just puzzling, it was, by more than one account in the literature, unsettling. The most detailed, most targeted study yet was still to come, and it was going to hit exactly the same wall, harder than anything before it. Part 5. The 2026 Infrared Dead End. By 2026, the investigation of LHAASO J2108+5157 had reached a critical juncture. The word juncture is doing real work in that sentence, because this was not simply another round of the same searches that had been failing for years. This was the moment when the scientific community had to make a choice about how to proceed. Every broad survey had failed. The wide-angle radio searches had turned up nothing. The X-ray campaigns had returned blank results. The preliminary optical and infrared checks had found no obvious candidates within the positional uncertainty region. 5 years of follow-up, conducted by multiple independent teams using facilities on multiple continents and in orbit, had produced a cumulative result that could be summarized in a single uncomfortable sentence: there is nothing there. What was needed at this stage was not another survey cast across a wide area, hoping to catch something in the net. What was needed was different in kind: a dedicated, methodical, deep targeted study using an instrument specifically configured for the task of looking through the dust and gas that might be obscuring whatever was generating the gamma-ray signal. Not a general search, a surgical one. That study was led by Joseph Marti and his collaborators, and it used the Cala Alto Observatory in the mountains of southeastern Spain. Cala Alto sits at an altitude of around 2,168 meters in the Sierra de los Filabres range, a ridge of mountains that rises above the dry plains of Almeria province in a region of Spain that receives some of the clearest skies in Europe. The observatory has operated there since the 1970s, and over the decades it has accumulated a track record in exactly the kind of careful, targeted observational work that this investigation required. For the Marti study, the primary instrument was the 2.2-meter telescope, configured specifically for deep infrared imaging and spectroscopic analysis of the LHAASO J2108+5157 target region. The configuration choices were deliberate and carefully reasoned, because the choice of infrared was not arbitrary. It was the product of thinking hard about what wavelength of observation gave the best chance of finding something that every previous search had missed. Here is the logic. The molecular clouds in the vicinity of LHAASO J2108+5157 contain enormous quantities of dust, microscopic, solid particles that are extraordinarily efficient at absorbing and scattering visible light. An object embedded within those clouds, whether a compact stellar remnant, an actively expanding shockwave, or an energetic binary system, would be hidden from optical telescopes by the intervening dust as completely as if a curtain had been drawn across it. But dust is not equally opaque at all wavelengths. At infrared wavelengths, particularly in the near-infrared and mid-infrared bands, dust becomes significantly more transparent. The longer wavelength infrared photons pass through dust columns that would be completely opaque to visible light. This is why astronomers routinely use infrared observations to study the insides of star-forming clouds, to image young stellar objects still surrounded by their birth material, and to examine the galactic centre, which is hidden behind so much dust that it is essentially invisible at optical wavelengths but accessible in infrared. If anything were hiding inside the dust around LHAASO J2108+5157, infrared was the wavelength most likely to find it. Infrared was, in a meaningful sense, the last serious option before the search would have to confront what it would mean to find absolutely nothing with the best available tool. The Marti team designed their observations around 3 specific categories of signature, each corresponding to a distinct physical scenario that could explain the gamma-ray emission. The first was shock-heated gas. When a supernova remnant expands into the surrounding interstellar medium, the shockwave at its leading edge slams into gas and compresses it violently, heating it to extreme temperatures. That heated gas does not just sit quietly. It radiates. It emits light at specific wavelengths corresponding to the electronic transitions of the atoms and ions in the shocked material, hydrogen recombination lines, forbidden line emission from ionized sulfur, ionized nitrogen, doubly ionized oxygen. In the infrared band, these lines are detectable even through substantial dust columns, and their presence is a definitive indicator of active shock activity. The intensity and ratios of these lines carry information about the shock velocity and the pre-shock gas density, allowing astronomers to characterize the shock wave even without directly imaging the object driving it. If a young supernova remnant were embedded in the molecular cloud and driving the peta-electron volt gamma ray emission through particle acceleration at its expanding shock front, this is exactly the signature that should appear, not faintly, not marginally. Clearly, because a remnant energetic enough to produce the observed gamma ray signal would be driving a shock wave powerful enough to produce line emission well above the detection threshold of a 2.2 meter infrared telescope. The second category was dust heating. Any energetic object embedded within a molecular cloud, whether a compact stellar remnant, an accreting binary, a young massive star, or something else entirely, will irradiate the surrounding dust with its emission. The dust grains absorb that radiation and re-emit the absorbed energy as thermal infrared emission, with a temperature and spectral shape that reflect the intensity and character of the irradiating source. This thermal infrared glow is how astronomers find embedded objects that are otherwise completely hidden. Point the telescope at the right place, look for an infrared excess, a region glowing warmer than the surrounding undisturbed cloud material, and you have a signpost pointing directly at the embedded energy source, even when the source itself cannot be directly imaged. If anything in the LHAASO region were depositing significant energy into its surroundings, the surrounding dust would be warm and it would glow in the infrared in a way that would be straightforward to detect and map. The third category was jet structures. The microquasar hypothesis, that the gamma-ray source is a compact binary system where a neutron star or black hole accretes material from a companion and launches relativistic jets, had been on the candidate list since early in the investigation. Microquasars are known particle accelerators, and their jets interact with the surrounding interstellar medium, driving shocks into the ambient gas and heating it. Those jet-medium interaction regions often produce extended structures, lobes, filaments, hotspots that are visible in radio and sometimes in infrared, even when the central compact object itself is not easily resolved. Searching for these extended structures in the infrared was a way to look for evidence of microquasar activity that might have been missed by radio surveys operating at different sensitivities or angular resolutions. Even if the core of the system were unresolved, the interaction of its jets with the surrounding cloud material might leave an infrared imprint large enough to detect. The observations were conducted. The data were reduced and analysed. The results came back. There were no nebula structures, no emission line regions with the spectral signatures of shocked gas, no infrared excess from heated dust, no extended lobe or filamentary structures associated with jet activity. The region, as seen through the infrared capabilities of the Alto 2.2 meter telescope, was essentially featureless. And that word, featureless, is important to sit with, because it is doing more work than it might appear to be doing. Featureless does not mean faint. It does not mean that signals were present but below the detection threshold, that with a larger telescope or longer exposure time, the team might have pulled something out of the noise. Featureless means the region looked like any ordinary unremarkable patch of sky, with no embedded energetic source and no ongoing energetic processes. It looked like nothing was happening there. This result carries more scientific weight than a simple failed detection. Infrared is not just another wavelength to check off a list and move past. It is specifically the wavelength regime engineered to defeat the obstacles, the dust, the opacity, the obscuration that cause other wavelengths to fail. When infrared returns empty results in a targeted deep observation, you have not just failed to find the source, you have eliminated a category of explanation. The absence of shocked gas emission rules out, with reasonable confidence, the scenario in which a young active supernova remnant is embedded in the molecular cloud and driving the gamma-ray emission. A remnant powerful enough to produce the observed signal would produce shocks powerful enough to produce detectable infrared line emission. No lines were found. The absence of dust heating emission rules out the presence of any highly luminous embedded source depositing significant energy into the surrounding medium. No dust glow was found. The absence of jet-associated structures removes the last remaining infrared accessible evidence for microquasar activity in the region. No jets were found. What the MARTI study accomplished, in the precise language of astrophysics, was to move the problem. Before the study, the operative question was whether the source was hidden, whether some combination of dust, distance, and observational geometry was conspiring to keep a known type of object out of view. That is a tractable problem. Hidden objects can be found with the right instruments and the right wavelengths. After the study, the question became something fundamentally different and fundamentally harder, because hidden objects leave traces. They heat the gas and dust around them. They drive shock waves into the interstellar medium. They blow bubbles and carve cavities in molecular clouds. They interact with their environments in ways that are detectable, even when the objects themselves cannot be directly imaged. The source of the LHAASO J2108+5157 gamma-ray emission is not doing any of those things, or if it is doing them at levels so far below what the physics predicts that the predictions themselves must be wrong. Whatever is generating peta-electron volt gamma rays in that direction is producing a confirmed, real, persistent effect on the surrounding molecular cloud material. The gamma rays are the proof of that, without producing any of the environmental side effects that physics says must accompany that level of energetic activity. The best instrument available for seeing through cosmic dust looked at this region carefully, thoroughly, and with a specific plan for what to find. It saw nothing. That is not a failure of the instrument, it is a result, and it is one of the most troubling results to emerge from high-energy astrophysics in recent memory. Part 6. The false lead that fooled everyone. In 2025, about midway through the multi-year investigation of LHAASO J2108+5157, something happened that briefly changed the tone of the research. Not dramatically, not with a press release or a headline. The change was quieter than that, more internal to the community, a shift in posture from grinding frustration towards something that felt cautiously like possibility. A team conducting radio observations of the region detected a source, a genuine, real, detectable radio signal coming from within the positional uncertainty region of the gamma-ray emission. After years of empty searches across every wavelength that astronomy could bring to bear, finding anything at all felt significant. The scientific community, quietly but perceptibly, began to lean forward. To understand why this detection generated the reaction it did, you need to appreciate the psychological texture of the investigation up to that point. Years of coordinated multi-wavelength searching had produced nothing. Not a marginal candidate that needed better data to confirm or rule out. Not an ambiguous detection that could be argued about. Nothing. The researchers involved in this investigation were not people who gave up easily. These are scientists who had dedicated significant portions of their careers to understanding the origins of the highest energy particles in the galaxy. But there is a particular kind of fatigue that comes from searching carefully and finding nothing repeatedly, and by 2025 that fatigue was present in the literature, readable between the lines of papers that kept reporting the same result in different wavelengths. The radio detection broke that pattern. Something was there. Something detectable, something that could be studied and characterized and either confirmed or ruled out through follow-up observation. That alone was enough to shift the mood. The detection also made sense on paper, which is part of why it generated the response it did. Radio emission is not a random or arbitrary thing to find in the vicinity of a peta-electron volt gamma-ray source. It is exactly what you would expect from the kinds of objects most likely to be responsible for emission at those energies. Compact binary systems, where a black hole or neutron star accretes material from a companion star, are among the most energetically efficient machines in the galaxy. The accretion process extracts gravitational potential energy from the infalling material and converts a significant fraction of it into radiation and into the kinetic energy of relativistic jets. Those jets, collimated streams of plasma moving at substantial fractions of the speed of light, generate synchrotron radio emission as the electrons in the jet spiral around the magnetic field lines threading through the jet material. The radio emission from these jets can be bright, structured, and detectable at large distances. Microquasars, which are the galactic-scale analogues of the much more powerful active galactic nuclei found at the centres of distant galaxies, are known radio emitters, known particle accelerators, and had been sitting near the top of the candidate list for this source since the initial 2021 detection. They can produce gamma rays, they produce radio emission, they fit the profile of what a pet-electron-volt gamma ray source might look like. When the radio source appeared within the positional uncertainty region of LHAASO J2108+5157, the natural and scientifically reasonable hypothesis was that this might finally be the microquasar responsible for the gamma ray signal, revealing itself after years of silence. Maybe the previous radio searches had been conducted at the wrong frequencies, or with insufficient sensitivity at the specific angular position of this object, or during a period when the source was in a quiescent state and its radio emission was below detectable levels. Compact binary systems are variable. They flare. They go quiet and then reactivate. It was entirely plausible that a source which had been radio dark during earlier searches might have brightened to detectable levels by 2025. The detection was real. The location was plausible. The physical scenario was coherent. The community leaned in. The follow-up analysis that came next was careful, rigorous, and ultimately devastating. Confirming that a radio source is the counterpart of a gamma ray source requires establishing two independent lines of evidence. The first is positional. The radio source and the gamma ray source must occupy the same location in the sky, within the uncertainties of both measurements. This sounds simple, but it is complicated by the fact that LHAASO's positional uncertainty for this source is not negligible. The gamma ray emission centroid has an uncertainty region that, at the distance of the source, corresponds to a physically large volume of space containing many possible objects. The radio telescope's positional precision is much better, so the question becomes whether the precisely measured radio position falls close enough to the less precisely measured gamma ray centroid to constitute a genuine positional coincidence rather than a chance alignment of two unrelated sources. The second line of evidence is spectral and morphological. The radio source's properties, the shape of its spectrum, its angular extent, its polarization characteristics, its variability, must be consistent with the type of galactic object being hypothesized. The team worked through both checks systematically. The positional comparison came first. When they refined the coordinates of the radio source using the full resolution of their radio data and compared those coordinates to the best available estimate of the gamma ray emission centroid, the match was not good enough. The offset between the radio position and the gamma ray position was larger than could be accounted for by combining the measurement uncertainties of both instruments in quadrature. In simpler terms, the radio source was not sitting where the gamma ray source was sitting, at least not within the margins of error that the data supported. In a field where positional coincidence is one of the primary tools for establishing physical associations between sources detected at different wavelengths, an offset of this magnitude is not a technicality, it is disqualifying. The spectral analysis deepened the problem further. When radio astronomers measure the spectrum of a source, the way its radio brightness varies as a function of frequency. The shape of that spectrum carries information about the physical processes generating the emission and the environment in which the source is embedded. Different types of objects have characteristically different spectral shapes. A pulsar wind nebula has a relatively flat or slightly inverted synchrotron spectrum at lower frequencies that steepens at higher frequencies. A compact binary system's jet typically produces a flat or slightly inverted spectrum over a wide frequency range. An extragalactic radio galaxy, powered by a supermassive black hole at its centre and observed from a distance of billions of light years, has its own characteristic spectral shape, often steep and with features related to the aging of the electron population in its radio lobes. The radio source found near LHAASO 2108+5157 had spectral properties that did not match a galactic compact object of any type. They matched an extragalactic background source, a radio galaxy, an object not 10,000 light-years away in the Milky Way, but billions of light-years away in the distant universe, its radio emission crossing cosmological distances before reaching Earth, its apparent position in the sky happening by pure geometric coincidence to fall within the same patch of sky as the LHAASO gamma-ray source. It was a false association. Not a mistake in the detection, the radio source was real and the measurement was accurate. But a cosmic coincidence of projection, the kind that happens routinely in astronomy when you're searching a region of sky that, viewed along that line of sight, contains not just the nearby structures of the Milky Way, but also the entire depth of the observable universe behind them. The radio source and the gamma-ray source were not physically connected in any meaningful way. They were separated by billions of light-years. The only relationship between them was the accident of direction. From Earth's vantage point, they happened to appear in the same part of the sky. The psychological impact of this correction on the research community was real and notable, in the understated way that emotional states tend to manifest in scientific contexts. Before the false lead, the researchers were frustrated but still actively engaged, still working through possibilities, still conducting searches. The discovery of the radio source had introduced something that had been largely absent from the investigation for years: a specific object to examine, a concrete candidate to test, a direction that felt like progress rather than the accumulation of further negative results. After the correction, the frustration acquired a new quality, because the false lead did not just fail to explain the gamma-ray source, it demonstrated, in a concrete and specific way, one of the most challenging aspects of this particular investigation. When your gamma-ray detection instrument cannot localize a source to better than a region tens of light-years across at the source distance, and when every other wavelength search within that region comes back empty, you face a problem that goes beyond simply needing more telescope time. You face the problem that even the detections you make can mislead you. Any source that happens to lie within the positional uncertainty region of the gamma-ray emission is a potential candidate. The universe behind those coordinates contains an enormous number of objects at all distances: stars, stellar remnants, background galaxies, radio sources at cosmological distances. Distinguishing a true physical association from a projection coincidence requires the kind of careful multi-parameter analysis that the team conducted here, and even that analysis, done correctly, ends in ruling out the only candidate that had emerged in years of searching. The invisible accelerator was not just invisible, it was, by this point in the investigation, actively resisting every attempt to make it visible. The one detection in years of searching had turned out to be a background galaxy billions of light-years away, with no physical connection to the source whatsoever. The mystery had not deepened in a productive direction, it had simply deepened. Part 7. The supernova that isn't there. From the beginning of the investigation, the hypothesis that generated the most scientific confidence, the explanation that felt most likely, the one that fit most naturally with established astrophysics, the one that senior researchers in the field would have bet on if betting were a standard part of the scientific process, was that LHAASO J2108+5157 was powered by a supernova remnant embedded within the nearby molecular clouds. This was not a wild guess reached by elimination or desperation. It was not a fringe idea proposed because nothing else came to mind. It was the product of a century of accumulated study of cosmic ray origins, built on some of the most carefully tested theoretical frameworks in all of high-energy astrophysics, and it fit the available evidence about as well as any hypothesis could fit evidence, when the evidence consists primarily of a gamma-ray signal and an absence of everything else. The argument for a supernova remnant as the driving source went like this. When a massive star, a star with at least 8 to 10 times the mass of the Sun, exhausts the nuclear fuel that has sustained it against gravitational collapse for millions of years, the core collapses catastrophically in a fraction of a second. The outer layers of the star, no longer supported by the outward pressure of the collapsing core, fall inward and then rebound in a shock wave of almost incomprehensible violence. The resulting explosion releases approximately 10 to the power of 44 joules of energy. That number is abstract to the point of meaninglessness without context, so consider this. It is roughly equivalent to the total energy output of the Sun over its entire 10 billion year lifespan, released not over billions of years but in a matter of seconds. The shockwave from that explosion expands outward into the surrounding interstellar medium at thousands of kilometers per second. At that speed, it would cross the distance from Earth to the Moon in less than 2 minutes. As that shockwave expands, it does something that is directly relevant to the mystery of LHAASO J2108+5157. It creates conditions for particle acceleration. Charged particles, protons, atomic nuclei, electrons become trapped in the turbulent magnetic field at the shock front and bounce back and forth across it repeatedly, gaining a small increment of energy with each crossing. This process, called diffusive shock acceleration, is one of the most well-understood mechanisms for producing high-energy particles in astrophysical environments. Over thousands of years, as the shock wave gradually decelerates by sweeping up the mass of the surrounding interstellar medium, the particles it has been accelerating accumulate to enormous energies. During the most energetic phase of the remnant's expansion, the phase when the shock is still moving fast and the magnetic field is still strong, the maximum energy achievable through this process approaches, and in the right conditions can reach, the peta-electron volt scale. The molecular clouds in the vicinity of LHAASO J2108+5157 complete the picture. Dense molecular clouds, sitting within reach of the accelerated proton population produced by the expanding remnant, act as targets. Accelerated protons stream outward from the remnant, penetrate the cloud material, and collide with the atomic nuclei in the cloud. Those collisions produce neutral pions, which decay almost immediately into pairs of gamma-ray photons. The result is a gamma-ray source illuminated by the cloud material, with the spectrum and intensity of the gamma rays encoding information about both the number and energy distribution of the accelerated protons striking the cloud. When astronomers looked at the gamma ray properties of LHAASO J2108+5157, the shape of the spectrum, the total luminosity, the spatial extent of the emission, the supernova remnant scenario reproduced those properties naturally. Everything about the setup seemed to fit. In 2023, a team went further than qualitative agreement and ran detailed quantitative simulations of the conditions required to reproduce the observed gamma-ray emission under the supernova remnant hypothesis. This kind of simulation work is important because it translates a general hypothesis into specific, testable predictions. The results place tight constraints on what the remnant would have to look like if it were real. It would need to be relatively young, less than 10,000 years old, because older remnants lose energy through processes that reduce their acceleration efficiency below the peta-electron volt threshold. 10,000 years is young by astrophysical standards, but it is not unusually young. Several known supernova remnants in the Milky Way fall in that age range, and they are among the most studied objects in high-energy astrophysics. The remnant would also need to be in close physical proximity to the molecular clouds, within roughly 200 light-years of the cloud material, to ensure that enough of the accelerated proton population reaches the cloud before dispersing. And it would need to be currently in an active phase of expansion, still driving a powerful shockwave through the surrounding medium, rather than having decelerated to a slow, cold shell. These constraints are not just theoretical parameters. They are observational predictions. Every specific requirement that the simulation placed on the hypothetical remnant corresponds directly to a physical signature that should be detectable with existing instruments. A supernova remnant less than 10,000 years old and still in an active expansion phase would produce a shell of radio emission surrounding the geometric center of the explosion. The relativistic electrons in the remnant spiral around the compressed magnetic field, swept up by the shock, radiating synchrotron emission that produces a characteristic shell morphology, bright at the edges where the line of sight through the shell is longest and dimmer toward the centre. This radio shell is not subtle. Known young remnants like Cassiopeia A, which is estimated to be roughly 350 years old, are among the brightest radio sources in the sky outside the solar system. Even less energetic remnants are detectable across large distances. A remnant capable of driving peta-electron volt acceleration should be radio bright. The same remnant would heat the surrounding interstellar medium to temperatures of tens of millions of degrees through the passage of the shockwave, producing diffuse X-ray emission detectable by space-based X-ray observatories across a region of sky corresponding to the physical extent of the shock-heated gas. X-ray emission from supernova remnants is one of the primary ways these objects are catalogued and studied. It would drive shock waves into the molecular cloud material at the interface between the expanding remnant and the cloud, generating the specific infrared emission lines from shock-heated gas that the MARTI study at Calar Alto was specifically designed to detect. Taken together, these signatures, radio shell, X-ray glow, infrared shock lines, form a mutually reinforcing set of evidence that any active, young, energetic supernova remnant should display clearly and simultaneously. None of those signatures were found. Not the radio shell, not the X-ray glow, not the infrared shock emission lines, not any combination of them. The region surrounding LHAASO J2108+5157 showed none of the expected observational evidence for an energetically active supernova remnant across any of the wavelengths where that evidence should appear. Scientists considered the obvious response to this absence. Could the remnant be hidden? Could there be enough absorbing material between the remnant and Earth that all of the expected signatures are suppressed before they reach our telescopes? This is a legitimate physical possibility in principle. The interstellar medium is not transparent. Dust absorbs visible light. Sufficiently dense gas columns can absorb soft X-rays. The molecular clouds in this region are genuinely dense, and a remnant embedded deeply within them could in principle be obscured at some wavelengths. But this is exactly where the infrared argument becomes not just relevant but decisive. Mid-infrared radiation can penetrate dust columns that are completely opaque to visible light and substantially opaque to soft X-rays. This is not a marginal improvement in transparency. It is the difference between seeing nothing and seeing clearly. If a hot, actively expanding supernova remnant were buried inside the molecular cloud complex near LHAASO J2108+5157, the dust surrounding it would be irradiated and heated by the remnant's emission, and that heated dust would re-emit the absorbed energy as thermal infrared radiation that would propagate outward through the cloud and be detectable by an infrared telescope even if the remnant itself could not be directly imaged. The Calar Alto infrared study by the MARTI team looked for exactly that signature: heated dust, warm emission, the infrared glow of an embedded energetic source, with an instrument specifically configured for that detection. There was nothing, not a faint excess, not an ambiguous warm region that might be attributed to a buried remnant. Nothing. The most parsimonious explanation for LHAASO J2108+5157, the explanation that requires the fewest departures from established physics, that invokes no new object classes or unknown processes, that sits most comfortably within a century of carefully built understanding of cosmic ray origins and supernova remnant physics, is quietly and systematically collapsing under the weight of the observations. A supernova remnant powerful enough to generate the observed peta-electron volt gamma ray emission should be detectable. Multiple deep targeted searches across multiple wavelengths confirm that it is not. Either the remnant exists but is behaving in ways that no known supernova remnant in the observed universe has ever been observed to behave, violating the predictions of the same physical models that make it a plausible candidate in the first place, or it does not exist at all. And if it does not exist, if the most conservative, most physically motivated, most theoretically grounded explanation for this source fails, then the investigation arrives at a question it has been approaching for 5 years and has now reached fully. What does fill the gap? The answers scientists are beginning to consider, carefully and with appropriate caution, are not the comfortable kind. Part 8. Why pulsars and black holes don't fit. If not a supernova remnant, the next obvious candidates are the compact objects that are often associated with the aftermath of stellar death. This is a natural progression in the investigation, because the same catastrophic event that produces the shockwave of a supernova remnant also leaves behind a dense stellar corpse. When a massive star exhausts its fuel and its core collapses, what remains depends on how much mass that core contains. Below a certain threshold, the collapse produces a neutron star, an object roughly the mass of the Sun compressed into a sphere about 20 kilometers across, so dense that a teaspoon of its material would weigh roughly 1 billion tons on Earth. Above that threshold, the collapse produces a black hole, an object whose gravity is strong enough that not even light can escape from within its boundary. Both of these objects are known particle accelerators. Both are present in environments capable of generating high-energy gamma-ray emission. Both have been identified as the driving engines behind gamma-ray sources elsewhere in the Milky Way. The natural question, after the supernova remnant hypothesis collapsed under the weight of the observational evidence, was whether one of them could be responsible here, operating somehow without the multi-wavelength signatures that every known example of these objects produces. And the natural answer, after careful examination of what the observations actually constrain, is no. Consider pulsars first, because pulsars are arguably the most compelling initial candidate. A pulsar is a neutron star that rotates rapidly, sometimes hundreds of times per second, and generates intense beams of electromagnetic radiation emanating from its magnetic poles. Because the magnetic axis of the neutron star is generally tilted relative to its rotation axis, those beams sweep across space with each rotation, like the beam of a lighthouse sweeping across the ocean. When that beam happens to point toward Earth during its sweep, observers detect a pulse of radio emission with extraordinary regularity. The precision of pulsar timing is so extreme that some pulsars keep time more accurately than the best atomic clocks on Earth. And this precision is itself one of the most useful properties of these objects. Astronomers use pulsar timing to probe the properties of matter at nuclear densities, to test general relativity in strong field regimes, and to search for low-frequency gravitational waves passing through the galaxy. Young, energetic pulsars do something beyond simply pulsing. They lose rotational energy continuously as they spin down, and a substantial fraction of that energy is channeled outward in the form of a wind, a flow of highly relativistic charged particles streaming away from the neutron star and inflating a bubble in the surrounding medium. This bubble, called a pulsar wind nebula, contains an enormous population of energetic electrons and positrons, spiraling in the compressed magnetic field at the edge of the bubble. Those particles produce gamma-ray emission through a process called inverse Compton scattering, where the high-energy electrons collide with low-energy photons, the cosmic microwave background, infrared photons from dust, optical photons from nearby stars, and boost those photons to gamma-ray energies in the collision. Pulsar wind nebulae are one of the primary known classes of high-energy gamma-ray sources in the Milky Way. The Crab Nebula, the remnant of a supernova observed by Chinese astronomers in 1054, is powered by a pulsar and is one of the most intensively studied objects in high-energy astrophysics. Its gamma-ray emission is understood well enough that it serves as a calibration standard for gamma-ray observatories. The pulsar scenario for LHAASO J2108+5157 would require a young energetic neutron star at the center of a wind nebula, injecting particles into the surrounding medium and driving gamma-ray emission at peta-electron volt energies. For this to work, the neutron star would need to be spinning fast enough and be young enough to still have the energy budget required. and here is where the observations impose a fatal constraint. Pulsars are not silent objects. They emit radio pulses, the sharp, periodic bursts of radio emission that define them as a class, and those pulses are detectable at large distances with modern radio telescopes. They also produce X-ray emission from the hot surface of the neutron star itself, which cools over thousands of years but remains detectable in X-rays for much of the relevant age range. The Pulsar Wind Nebula produces diffuse X-ray emission from synchrotron radiation, as electrons spiral in the nebula's magnetic field, and this extended X-ray nebulosity is one of the most reliable observational signatures of an active pulsar wind system. No radio pulsations have been detected in the direction of LHAASO J2108+5157, despite radio searches sensitive enough to find a wide range of known pulsar types. No X-ray point source has been found at a position consistent with the gamma-ray emission. No diffuse X-ray emission consistent with a pulsar wind nebula has been detected. The pulsar hypothesis requires a specific type of object to be present and energetically active in this region. The observations say it is not there. Black hole binaries present a different version of the same problem. These systems consist of a black hole, typically with a mass between 5 and 20 solar masses for the galactic examples, though the range extends considerably in some cases in a close orbit with a companion star. Material from the companion flows toward the black hole, forms an accretion disk, and releases an enormous amount of gravitational potential energy in the process. The accretion disk heats to temperatures of tens of millions of degrees and radiates intensely in X-rays. In many of these systems, a fraction of the accreting material is redirected into relativistic jets, collimated outflows of plasma moving at substantial fractions of the speed of light that produce synchrotron radio emission and sometimes contribute to gamma-ray production as well. When these systems are in an active accretion state, they are among the brightest X-ray sources in the galaxy, detectable with ease by X-ray satellites even at the distances relevant to LHAASO J2108+5157. Finding a black hole binary that is somehow generating peta-electron-volt gamma-ray emission, while simultaneously producing no detectable X-ray emission from the accretion disk, no detectable radio emission from the jets, and no thermal signatures of any kind would not just be unusual. It would require the accretion physics that governs these systems to be wrong in ways that nothing in the existing observational literature hints at. It would effectively constitute a new class of object rather than a known one, which means invoking it as an explanation is not actually an explanation at all. Magnetars deserve a brief but honest assessment. A magnetar is a neutron star with a magnetic field so intense, roughly 1,000 times stronger than that of an ordinary pulsar, that the magnetic energy itself drives extreme physical processes at and near the stellar surface. Magnetars produce outbursts of high-energy emission, primarily in X-rays and soft gamma rays, that can briefly make them among the most luminous objects in the galaxy. They are fascinating and in some respects still poorly understood objects, but they are emphatically not quiet. Their defining characteristic is energetic, often dramatic emission activity. The absence of any X-ray or high-energy transient signal in the LHAASO J2108+5157 region over the years of monitoring that have accompanied this investigation rules out an active magnetar as the source. A magnetar would have announced itself. Step back from the individual candidates and look at the pattern. What the elimination of pulsars, black hole binaries, magnetars, and supernova remnants reveals is not just that specific objects fail to fit. It reveals something more structural about the problem. Every known category of compact astrophysical object that could plausibly drive peta-electron-volt gamma-ray emission has characteristic observational signatures, specific, well-understood byproducts of the physical processes that give these objects their energy and their ability to accelerate particles. Pulsars pulse and build wind nebulae. Black hole binaries accrete and radiate and launch jets. Supernova remnants expand and shock and heat. Magnetars flare and burst. In each case, the energy that goes into particle acceleration is accompanied by energy going into electromagnetic radiation across multiple wavelengths, because the physics that enables acceleration in these environments inevitably also produces radiation as a byproduct. This is not a coincidence or a design flaw. It is a consequence of thermodynamics and electromagnetism. Energy deposited into a population of charged particles in a magnetic field does not stay neatly in the particles, it leaks into radiation. Electrons radiate synchrotron emission. Hot gas radiates thermally. Shock waves heat material that then cools by radiating. The universe does not produce powerful particle accelerators that are electromagnetically invisible. It never has, in the entire catalogue of sources that astronomy has assembled over more than a century of observation. And yet here, in the direction of LHAASO J2108+5157, none of those leaks appear. Every known category has been tested against the observations and found to fail. Every candidate has been examined and dropped. The investigation has worked through the entire list of objects that astrophysics can offer as explanations for a source of this energy, and none of them fit. What remains, the only thing that remains, is the signal itself. Powerful, real, persistent, and completely without a known source. The hidden accelerator in our own galaxy has now survived the systematic elimination of every known class of astrophysical object that could explain it. What comes next is not territory that existing frameworks handle comfortably. Part 9. The Dark Accelerator Problem. When every known explanation fails, scientists do not immediately reach for the exotic. That is not how science works, and it is not how scientists think, at least not the careful ones whose conclusions survive long enough to matter. The first response to a result that defies existing frameworks is not excitement about new physics, it is methodological skepticism. Rigorous, systematic, occasionally tedious methodological skepticism. Go back to the data, check the assumptions embedded in the analysis, look for errors in the reduction pipeline, re-examine whether the constraints are really as tight as they appear, or whether some combination of measurement uncertainty and modelling assumptions has made the situation look more impossible than it actually is. Ask whether the non-detections at other wavelengths are genuine non-detections, or whether the searches were sensitive enough to rule out the relevant scenarios. This process takes time, and it is genuinely valuable. It is precisely how mistakes get caught before they calcify into the literature and mislead an entire field for a decade. But in the case of LHAASO J2108+5157, this process has been running for 5 years. Multiple independent teams have gone back to the data. Multiple instruments have repeated the searches with improved sensitivity. Multiple rounds of analysis have tested and retested the constraints. Papers have been written, reviewed, challenged, and defended. And the conclusion keeps returning the same result, stated in different words by different authors, but amounting to the same thing every time. The signal is real. The source is invisible. The known explanations do not work. At some point, continued methodological skepticism stops being rigor and starts being avoidance. That point has been reached, and so scientists have begun, carefully and with appropriate caution, and with the kind of hedged language that reflects genuine intellectual discomfort, to engage with a concept that is genuinely new, the idea of a dark accelerator. It is worth being precise about what that term means and what it does not mean, because precision matters here, and the word dark carries baggage in astronomy that can mislead. This is not dark in the sense of dark matter, the hypothetical non-luminous mass component that makes up roughly 27% of the universe's energy density, and that physicists have been searching for directly since the 1980s. The connection to dark matter is not entirely absent from some of the more speculative corners of the literature, and we will come back to that, but it is not the primary meaning. Dark accelerator means dark in the most literal, operational, observational sense of the word. An astrophysical object that accelerates particles to pitter electron volt energies and produces essentially no electromagnetic radiation through its own physical processes. No synchrotron emission from relativistic electrons spiraling in magnetic field lines. No thermal radiation from heated gas surrounding the acceleration region. No non-thermal X-rays from inverse Compton scattering. No radio emission from jets. No infrared glow from heated dust. Nothing. Just the secondary gamma rays produced when the accelerated protons travel outward and slam into the nuclei of atoms in the nearby molecular cloud material. And even those gamma rays are not the source's own emission. They are the emission of the cloud, excited by the source's output. The problem with this concept is not that it is logically impossible. Logical impossibility would actually be easier to deal with, because you could simply rule it out and keep searching for something that fits within existing frameworks. The problem is more subtle and more uncomfortable than impossibility. The problem is that our current theoretical models do not predict it. They do not even approach predicting it. In the standard framework for understanding particle acceleration in astrophysical plasmas, the framework built up over decades of theoretical work and tested against hundreds of observed sources, the processes that boost charged particles to high energies almost invariably produce synchrotron radiation as an unavoidable byproduct. The reason is straightforward. Astrophysical plasmas almost always contain both protons and electrons. Electrons are light, roughly 1,836 times lighter than protons, and light-charged particles in magnetic fields radiate efficiently. The power radiated by a charged particle through synchrotron emission scales as the square of the particle's energy divided by the square of its mass. For electrons at high energies in a magnetic field, synchrotron radiation is not a minor side effect. It is a dominant energy loss mechanism. You cannot accelerate electrons in a magnetized plasma to high energies and avoid producing synchrotron emission. The physics does not allow it, and yet this source appears to be doing exactly that. Several ideas have been discussed in the literature in an attempt to construct a physically plausible model for a dark accelerator, and it is worth working through them honestly, including their limitations, because the limitations are as informative as the ideas themselves. The most physically grounded possibility is that the source is accelerating primarily protons rather than electrons. The mass difference between protons and electrons has a direct consequence for synchrotron radiation. Because synchrotron power scales inversely with the square of the particle mass, a proton radiates synchrotron emission at a level roughly 3 million times weaker than an electron of the same energy in the same magnetic field. A proton accelerator operating at peta-electron volt energies would produce synchrotron emission, but the emission would fall at radio wavelengths and at a luminosity potentially far below the detection threshold of current radio surveys. This is a physically coherent idea. It would explain why the radio searches have returned nothing. Proton-dominated acceleration is not without precedent. There is an ongoing debate in the field about whether the gamma-ray emission from certain supernova remnants is predominantly hadronic, meaning proton-driven, or leptonic, meaning electron-driven, and hadronic scenarios are taken seriously. But the proton-dominated hypothesis does not resolve the full problem. It addresses the radio silence. It does not easily address the thermal silence. Any energetically significant astrophysical object embedded in or near a molecular cloud will interact with the surrounding gas and dust through processes beyond just particle acceleration. Shock heating, radiation pressure, energetic particle bombardment of the cloud surface. These interactions deposit energy into the surrounding medium, and that energy has to go somewhere. It goes into heat, and heated material radiates. Even a source that produces no direct electromagnetic emission of its own would heat its environment, and that heated environment should glow, particularly in the infrared. The Alto infrared study found no such glow. The proton-dominated scenario explains one silence, but not all of them. The second possibility involves unusual magnetic field configurations in the acceleration region. Standard synchrotron emission is most efficient when the magnetic field is tangled and turbulent, because tangled fields expose electrons to a wide range of field directions and magnitudes, maximizing the conditions for efficient radiation. If the magnetic field in the acceleration region were instead highly ordered and laminar, structured in a way that channels accelerated particles along field lines without creating the turbulent conditions that generate strong synchrotron emission, it might be possible to construct an accelerator that is electromagnetically quieter than standard models predict. Ordered magnetic field geometries have been discussed in other astrophysical contexts, and there is nothing in the laws of physics that forbids them. But this idea remains entirely speculative. There is no confirmed observational analogue for an acceleration region with this combination of properties, high energy output, ordered magnetic geometry, and suppressed radiation across all wavelengths simultaneously. It is a possibility in the sense that it cannot be immediately ruled out. It is not a possibility in the sense of having any supporting evidence. Think carefully about what either of these scenarios would mean if one of them were true. A machine operating at the highest particle energies in the galaxy, in our own galaxy, detectable only because it happens to sit near enough to a molecular cloud that the protons it produces have something to collide with. Remove the cloud, move this object to an emptier region of the interstellar medium, and the secondary gamma rays disappear. The protons disperse freely into space. The object produces nothing detectable, nothing at all. We would have no knowledge it existed. That thought leads somewhere genuinely uncomfortable. How many objects like this might exist in regions of the galaxy where there are no molecular clouds in the right position to act as targets? How many peta-electron volt accelerators could be running right now in the Milky Way, in the spiral arms, in the interarm regions, in the outer galaxy, producing no secondary gamma rays because there is no gas for their proton output to collide with, leaving no traces of any kind, remaining completely outside our knowledge, not because they are faint, but because the indirect detection mechanism we rely on requires a specific environmental condition that may not always be present. This is no longer a question about one anomalous source in one unusual location. This is a question about the fundamental completeness of our census of the galaxy's high-energy objects. And the answer implied by LHAASO J2108+5157 is that our census may be profoundly incomplete in ways we cannot currently quantify, because we do not know how many of these objects there are or where they are or what they are. The mystery has shifted in character over the 5 years of this investigation. It began as a detection problem. We found a signal. We need to find the source. It progressed through an identification problem. We have searched and found nothing. We need to understand why. And it has arrived, finally, at something deeper. A physics problem. A problem about whether our current theoretical models of particle acceleration in astrophysical environments are complete, or whether they are missing something important. Something that operates at the highest energies accessible in our galaxy, that leaves no electromagnetic signature of its own existence, and that our models do not predict and cannot yet describe. The shift from an unexplained observation to a potential gap in fundamental physics is not a minor escalation. It is the difference between a mystery that existing tools might eventually solve and a mystery that might require new tools, new frameworks, and new ways of thinking about what kinds of things the universe is allowed to contain. Part 10. A new kind of object. When every known explanation fails, scientists do not immediately reach for the exotic. That is not how science works, and it is not how scientists think, at least not the careful ones whose conclusions survive long enough to matter. The first response to a result that defies existing frameworks is not excitement about new physics. It is methodological skepticism. Rigorous, systematic, occasionally tedious methodological skepticism. Go back to the data. Check the assumptions embedded in the analysis. Look for errors in the reduction pipeline. Re-examine whether the constraints are really as tight as they appear, or whether some combination of measurement uncertainty and modelling assumptions has made the situation look more impossible than it actually is. Ask whether the non-detections at other wavelengths are genuine non-detections, or whether the searches were sensitive enough to rule out the relevant scenarios. This process takes time, and it is genuinely valuable. It is precisely how mistakes get caught before they calcify into the literature and mislead an entire field for a decade. But in the case of LHAASO J2108+5157, this process has been running for 5 years. Multiple independent teams have gone back to the data. Multiple instruments have repeated the searches with improved sensitivity. Multiple rounds of analysis have tested and retested the constraints. Papers have been written, reviewed, challenged, and defended. And the conclusion keeps returning the same result, stated in different words by different authors, but amounting to the same thing every time. The signal is real. The source is invisible. The known explanations do not work. At some point, continued methodological skepticism stops being rigour and starts being avoidance. That point has been reached, and so scientists have begun, carefully and with appropriate caution, and with the kind of hedged language that reflects genuine intellectual discomfort, to engage with a concept that is genuinely new, the idea of a dark accelerator. It is worth being precise about what that term means and what it does not mean, because precision matters here, and the word dark carries baggage in astronomy that can mislead. This is not dark in the sense of dark matter, the hypothetical non-luminous mass component that makes up roughly 27% of the universe's energy density, and that physicists have been searching for directly since the 1980s. The connection to dark matter is not entirely absent from some of the more speculative corners of the literature, and we will come back to that, but it is not the primary meaning. Dark accelerator means dark in the most literal, operational, observational sense of the word. An astrophysical object that accelerates particles to peta-electron volt energies and produces essentially no electromagnetic radiation through its own physical processes. No synchrotron emission from relativistic electrons spiraling in magnetic field lines. No thermal radiation from heated gas surrounding the acceleration region. No non-thermal X-rays from inverse Compton scattering. No radio emission from jets. No infrared glow from heated dust. Nothing. Just the secondary gamma rays produced when the accelerated protons travel outward and slam into the nuclei of atoms in the nearby molecular cloud material. And even those gamma rays are not the source's own emission. They are the emission of the cloud, excited by the source's output. The problem with this concept is not that it is logically impossible. Logical impossibility would actually be easier to deal with, because you could simply rule it out and keep searching for something that fits within existing frameworks. The problem is more subtle and more uncomfortable than impossibility. The problem is that our current theoretical models do not predict it. They do not even approach predicting it. In the standard framework for understanding particle acceleration in astrophysical plasmas, the framework built up over decades of theoretical work and tested against hundreds of observed sources, the processes that boost charged particles to high energies almost invariably produce synchrotron radiation as an unavoidable byproduct. The reason is straightforward. Astrophysical plasmas almost always contain both protons and electrons. Electrons are light, roughly 1,836 times lighter than protons, and light-charged particles in magnetic fields radiate efficiently. The power radiated by a charged particle through synchrotron emission scales as the square of the particle's energy divided by the square of its mass. For electrons at high energies in a magnetic field, synchrotron radiation is not a minor side effect. It is a dominant energy loss mechanism. You cannot accelerate electrons in a magnetized plasma to high energies and avoid producing synchrotron emission. The physics does not allow it, and yet this source appears to be doing exactly that. Several ideas have been discussed in the literature in an attempt to construct a physically plausible model for a dark accelerator, and it is worth working through them honestly, including their limitations, because the limitations are as informative as the ideas themselves. The most physically grounded possibility is that the source is accelerating primarily protons rather than electrons. The mass difference between protons and electrons has a direct consequence for synchrotron radiation. Because synchrotron power scales inversely with the square of the particle mass, a proton radiates synchrotron emission at a level roughly 3 million times weaker than an electron of the same energy in the same magnetic field. A proton accelerator operating at peta-electron volt energies would produce synchrotron emission, but the emission would fall at radio wavelengths and at a luminosity potentially far below the detection threshold of current radio surveys. This is a physically coherent idea. It would explain why the radio searches have returned nothing. Proton-dominated acceleration is not without precedent. There is an ongoing debate in the field about whether the gamma-ray emission from certain supernova remnants is predominantly hadronic, meaning proton-driven, or leptonic, meaning electron-driven, and hadronic scenarios are taken seriously. But the proton-dominated hypothesis does not resolve the full problem. It addresses the radio silence. It does not easily address the thermal silence. Any energetically significant astrophysical object embedded in or near a molecular cloud will interact with the surrounding gas and dust through processes beyond just particle acceleration. Shock heating, radiation pressure, energetic particle bombardment of the cloud surface. These interactions deposit energy into the surrounding medium, and that energy has to go somewhere. It goes into heat, and heated material radiates. Even a source that produces no direct electromagnetic emission of its own would heat its environment, and that heated environment should glow, particularly in the infrared. The Palo Alto infrared study found no such glow. The proton-dominated scenario explains one silence but not all of them. The second possibility involves unusual magnetic field configurations in the acceleration region. Standard synchrotron emission is most efficient when the magnetic field is tangled and turbulent, because tangled fields expose electrons to a wide range of field directions and magnitudes, maximizing the conditions for efficient radiation. If the magnetic field in the acceleration region were instead highly ordered and laminar, structured in a way that channels accelerated particles along field lines without creating the turbulent conditions that generate strong synchrotron emission, it might be possible to construct an accelerator that is electromagnetically quieter than standard models predict. Ordered magnetic field geometries have been discussed in other astrophysical contexts, and there is nothing in the laws of physics that forbids them. But this idea remains entirely speculative. There is no confirmed observational analogue for an acceleration region with this combination of properties, high energy output, ordered magnetic geometry, and suppressed radiation across all wavelengths simultaneously. It is a possibility in the sense that it cannot be immediately ruled out. It is not a possibility in the sense of having any supporting evidence. Think carefully about what either of these scenarios would mean if one of them were true. A machine operating at the highest particle energies in the galaxy, in our own galaxy, detectable only because it happens to sit near enough to a molecular cloud that the protons it produces have something to collide with. Remove the cloud, move this object to an emptier region of the interstellar medium, and the secondary gamma rays disappear. The protons disperse freely into space. The object produces nothing detectable, nothing at all. We would have no knowledge it existed. That thought leads somewhere genuinely uncomfortable. How many objects like this might exist in regions of the galaxy where there are no molecular clouds in the right position to act as targets? How many peta-electron volt accelerators could be running right now in the Milky Way, in the spiral arms, in the interarm regions, in the outer galaxy, producing no secondary gamma rays because there is no gas for their proton output to collide with, leaving no traces of any kind, remaining completely outside our knowledge, not because they are faint, but because the indirect detection mechanism we rely on requires a specific environmental condition that may not always be present. This is no longer a question about one anomalous source in one unusual location. This is a question about the fundamental completeness of our census of the galaxy's high-energy objects. And the answer implied by LHAASO J2108+5157 is that our census may be profoundly incomplete in ways we cannot currently quantify, because we do not know how many of these objects there are or where they are or what they are. The mystery has shifted in character over the 5 years of this investigation. It began as a detection problem. We found a signal, we need to find the source. It progressed through an identification problem. We have searched and found nothing. We need to understand why. And it has arrived finally at something deeper, a physics problem. A problem about whether our current theoretical models of particle acceleration in astrophysical environments are complete, or whether they are missing something important. Something that operates at the highest energies accessible in our galaxy, that leaves no electromagnetic signature of its own existence, and that our models do not predict and cannot yet describe. The shift from an unexplained observation to a potential gap in fundamental physics is not a minor escalation. It is the difference between a mystery that existing tools might eventually solve and a mystery that might require new tools, new frameworks, and new ways of thinking about what kinds of things the universe is allowed to contain. Part 11. The Hidden Population Hypothesis. The unsettling possibility that scientists have begun to take seriously is that LHAASO J2108+5157 is not unique. It may not even be rare. And if that sentence does not immediately strike you as one of the more disorienting things you have heard in the context of this investigation, sit with it for a moment, because the implications of it unspool in directions that touch not just on this one source, but on the entire framework astronomers use to understand the high-energy environment of the galaxy we live in. To understand why this possibility arises, you need to think carefully and specifically about why we were able to detect this object at all. The answer is not that it is particularly bright or close, or that it produces an unusually strong signal by the standards of its class. The answer is circumstantial. The gamma-ray signal from LHAASO J2108+5157 is detectable because the source happens to be located near dense molecular cloud material. The accelerated protons produced by whatever the source is travel outward from the acceleration region into that cloud material, collide with the nuclei of atoms in the cloud, and generate the secondary gamma rays that LHAASO's detector arrays capture when those gamma rays reach Earth and initiate particle showers in the atmosphere. The detection chain depends entirely on that collision. Take away the molecular cloud, move it somewhere else in the galaxy, or move the source to a location not adjacent to dense gas, and the protons disperse freely into the lower density interstellar medium surrounding the cloud. The collision rate drops, the secondary gamma ray production drops with it. The signal falls below the detection threshold, or disappears entirely. The source becomes, in every observational sense, completely undetectable, not difficult to detect, not faint but measurable with a larger facility. Undetectable in principle, because the indirect detection mechanism that reveals its existence requires a specific environmental condition that is no longer present. This is a different kind of invisibility than what the failed multi-wavelength searches revealed. Those searches showed that the source produces no direct electromagnetic emission of its own. This additional consideration shows that even the indirect detection method we actually used to find it depends on a cosmic accident of geometry. The source is detectable only because it is near a cloud. It is known to us only because of where it happens to sit in the galaxy. Change the location and we never find it. Now consider the structure of the Milky Way and what that implies. The galaxy contains an enormous reservoir of molecular cloud material. The molecular zones concentrated in the inner galaxy, within a few thousand light years of the galactic center, hold millions of solar masses of dense cold gas distributed across layered, complex cloud structures that span hundreds of light years in some cases. The spiral arms of the galaxy, which is where most star formation occurs, are threaded with molecular clouds at regular intervals. Star-forming regions throughout the galactic disk extend this reservoir across a wide range of distances and directions from Earth. Molecular clouds are not exotic or unusual environments in the Milky Way. They are among the most common large-scale structures in the galaxy. The galactic plane, viewed from above, would show them clustered along the spiral arms in a pattern that covers a substantial fraction of the disk's area. This matters because it means the detection scenario that allowed us to find LHAASO J2108+5157, a pevatron positioned near a molecular cloud, its proton output colliding with the cloud material and generating detectable secondary gamma rays, is not a uniquely improbable configuration. It is a configuration that could repeat wherever a dark accelerator happens, to sit near one of the many molecular cloud complexes distributed across the galaxy. The question is not whether such configurations exist. Given how common molecular clouds are, they almost certainly exist in multiple places. The question is how many dark accelerators there are, and what fraction of them happen to sit near clouds dense enough and close enough to produce a gamma ray signal strong enough to detect. This is where the concept of detection bias enters the picture, and it is important to understand what that term means in this context. A detection bias is a systematic effect that causes your observed sample to be unrepresentative of the true underlying population. It does not mean your measurements are wrong. It means your measurements are correct but incomplete in a structured way. The objects you can find are a specific subset of all the objects that exist, selected by conditions that have nothing to do with how common those objects are. In this case, the detection bias is geometric and environmental. You can detect dark accelerators only when they are positioned near molecular clouds, dense enough to produce significant secondary gamma ray emission. Dark accelerators that are not near such clouds cannot be detected with any current method. This means the population of dark accelerators you can observe is a subset, selected by proximity to molecular cloud material, of the true total population. Apply basic statistical reasoning to this. Currently, the number of confirmed non-luminous pevatrons is 1. That is the entire observed sample. If the fraction of all dark accelerators in the galaxy that happen to sit near detectable molecular cloud material is something like 10 to 20%, a rough but not implausible range, given what we know about the distribution of molecular clouds and the likely distribution of whatever class of object this represents, then the total population implied by finding one example is somewhere between 5 and 10 objects. But this estimate is conservative in an important way. It assumes the detection bias depends only on whether a molecular cloud is nearby at all. In reality, the bias is more complex. It depends on the density of the cloud material, because denser clouds produce more collisions and stronger gamma ray signals. It depends on the physical separation between the accelerator and the cloud, because protons disperse as they travel, and a source far from the cloud illuminates it less efficiently than one embedded within it. It depends on the distance from Earth, because the sensitivity of gamma ray observations decreases with distance. When you account for all these additional factors, the implied true population expands further. The number of dark accelerators in the galaxy consistent with detecting exactly one of them under current observational conditions could be substantially larger than the simple geometric estimate suggests. There is something genuinely disorienting about following this reasoning to its conclusion. The Milky Way may contain a population of invisible, extraordinarily powerful particle accelerators that cannot be detected, cannot be imaged, cannot be characterized, and would be entirely unknown to science if a specific and somewhat accidental combination of circumstances had not placed one of them near a molecular cloud in a direction accessible to LHAASO. The one example we have found may be the lucky exception, the single member of a larger hidden population that happened to satisfy the right geometric conditions at the right distance and in the right direction for detection to be possible. And every other member of that population, sitting in regions of the galaxy without the right cloud geometry, or at distances too great for current instruments, or in directions not yet surveyed with sufficient sensitivity, is by the logic of the detection bias completely hidden from us. We are not even counting them. We do not know they exist. There is no list with blank entries awaiting confirmation. There is just absence, which we have no current way to distinguish from the absence of the objects themselves. The implications for the cosmic ray origin problem specifically are significant enough to deserve careful attention. The question of where galactic cosmic rays come from, where the high-energy particles that continuously rain down on Earth's atmosphere are produced and accelerated, has been one of the central open problems in astrophysics for over a century. The standard answer, developed over decades of theoretical and observational work, involves supernova remnants as the primary sources, with various secondary contributors including pulsars, stellar winds, and other energetic environments. The energy budget of galactic cosmic rays has been constructed by adding up the contributions from known source populations and checking whether the total matches the observed cosmic ray flux at Earth and the inferred production rate needed to maintain that flux against losses and escape from the galaxy. If dark accelerators are producing cosmic rays throughout the galaxy, and if those accelerators are predominantly invisible to current instruments, then that energy budget has a missing term. The accounting is incomplete in a systematic way. The models built on the existing census of sources may be missing a contributor that has never been included because it has never been identified. The total energy going into galactic cosmic ray production may be higher than current estimates, or the contributions attributed to known sources may need to be revised downward to accommodate the hidden contribution of dark accelerators. Either way, a century of careful work on this problem would need to be revisited. And then there is the final layer of this, the one that feels most immediate and most strange when you really sit with it. The cosmic rays that dark accelerators produce throughout the galaxy are not staying out there. Cosmic rays propagate. They diffuse through the galaxy's magnetic field over timescales of millions of years, gradually spreading from their production sites. If dark accelerators exist in significant numbers across the Milky Way, the cosmic rays they produce are reaching Earth. They are arriving at the top of the atmosphere right now, as you read this, as part of the continuous particle rain that physicists have been measuring at ground-based observatories for over 100 years. Some fraction of those particles, we do not know how large a fraction, because we do not know how many dark accelerators there are, originated from objects we have never seen, never identified, and cannot currently characterize. The galaxy's most powerful engines may be running in complete silence, hidden not by distance or dust or any of the conventional obstacles that astronomy has learned to overcome, but by a more fundamental absence. They produce no light of any kind. They announce their existence only through particles, and the only reason we know even one of them exists is because one of them happened to park itself next to a cloud. Part 12. The limit of our vision. There is an instrument being built that will push the investigation of sources like LHAASO J2108+5157 further than any existing facility can reach. It is worth understanding what that instrument is, what it will genuinely be able to do, and, with equal honesty, where its capabilities end and the fundamental problem begins. Because there is a difference between a technological limitation and a conceptual one, and in the case of this investigation, that difference matters more than it usually does. The Cherenkov Telescope Array, known as the CTA, is an international project decades in the making, involving institutions from more than 30 countries and representing the most ambitious ground-based gamma-ray observatory ever attempted. It will operate two separate arrays of imaging atmospheric Cherenkov telescopes, one at La Palma in the Canary Islands in the Northern Hemisphere, and one at the Paranal site in the Atacama Desert of Chile in the Southern Hemisphere. The geographic split is deliberate. Different regions of the sky are accessible from different latitudes, and operating complementary arrays on both sides of the equator maximizes the fraction of the sky that can be observed. The northern array will be optimized for the lower end of the very high-energy gamma-ray spectrum, where the Cherenkov imaging technique is most effective for certain source classes. The southern array will extend to the highest energies accessible to ground-based observation, which is the regime most relevant to peta-electron volt sources like LHAASO J2108+5157. The performance improvement over current generation instruments is real and meaningful. Compared to existing imaging Cherenkov telescope arrays, the CTA will achieve angular resolutions roughly 3 to 5 times better across the relevant energy range. To understand what that means in practice, recall the positional uncertainty problem that has plagued this investigation from the beginning. LHAASO can tell you the direction of a gamma-ray source to within a fraction of a degree, which at the estimated distance of 10,000 light-years translates into a physical search region tens of light-years across, a volume containing many possible counterpart objects and creating exactly the kind of ambiguity that allowed a background radio galaxy to appear as a plausible candidate before being ruled out. CTA's improved angular resolution narrows that uncertainty region substantially. A 3 to 5 times improvement in angular precision means the search area for a counterpart object shrinks by a factor of 9 to 25. That is not a marginal gain. That is the difference between searching a city and searching a neighborhood. For LHAASO J2108+5157 specifically, this improvement could matter in ways beyond simply narrowing the counterpart search area. If the gamma-ray emission from this source has internal structure, if it is not a smooth, featureless blob but contains multiple distinct emission peaks, or shows concentration toward a particular subregion of the molecular cloud complex, or reveals an asymmetry that points toward the location of the accelerating source, CTA observations would have the resolution to reveal that structure where LHAASO cannot. Internal structure in the gamma-ray emission would carry physical information. It would tell you something about the geometry of the proton injection, the distribution of the cloud material acting as the target, and potentially the location of the source within the cloud. A smaller, better constrained uncertainty region also reduces the probability that any counterpart detected at other wavelengths is a chance background coincidence rather than a genuine physical association, the problem that turned the 2025 radio detection into a false lead rather than a breakthrough. So yes, CTA represents genuine progress. It is a real and important step forward for the investigation of this source and for high-energy gamma-ray astronomy more broadly. Anyone who tells you it is irrelevant to this mystery is wrong. But there is a fundamental limitation that better angular resolution cannot address. It is the limitation that sits at the centre of this entire investigation, and it is important to state it clearly rather than allow the excitement about a new instrument to obscure it. CTA is still a gamma-ray instrument. It detects gamma rays through the same basic process that LHAASO uses, the reconstruction of atmospheric particle showers initiated by incoming gamma-ray photons. It still relies on detecting the secondary gamma rays produced by cosmic ray interactions with molecular cloud gas. The gamma rays are not the source's own emission. They are the emission of the cloud material, excited by the protons that the source produces. If the source itself produces no electromagnetic radiation through its own physical processes, if it is genuinely a dark accelerator in the operational sense that 5 years of investigation suggests, then CTA will see the same fundamental thing that LHAASO sees. The contours of the emission region will be sharper, the position will be better constrained, the internal structure, if it exists, will be resolved. But the source, the actual object driving all of this, will still not be visible. Better eyes do not help you find something that emits no light. And this is the edge. The real edge. Not the edge of what a particular instrument can do, or what current technology allows, or what this generation of scientists can accomplish with the resources available to them. This is the edge of what a particular approach to understanding the universe can achieve. Electromagnetic astronomy, the study of everything beyond Earth through the detection of light in all its forms, from radio waves with wavelengths measured in meters to gamma rays with wavelengths smaller than an atomic nucleus, has been the foundation of essentially everything humanity knows about the universe. Every galaxy in the catalogues, every star with a measured spectrum, every neutron star and black hole and nebula, a molecular cloud and stellar nursery and supernova remnant in our understanding of the cosmos was discovered and characterized through the detection of electromagnetic radiation. Light is how we see. Light is how we know. It is the only messenger we have used for the entire history of observational astronomy that has never failed to eventually reveal something. The assumption embedded in every telescope ever built, in every survey ever conducted, in every multi-wavelength campaign ever coordinated, is that the things worth finding radiate, that the universe's objects and processes announce their existence through electromagnetic emission of some kind, at some wavelength, at some detectable level. This assumption has been so consistently correct across so many different types of objects and environments and energy scales that it stopped being an assumption a long time ago. It became a foundation, something you build on without examining it because it has never cracked. LHAASO J2108+5157 is putting a crack in it. If this source is what the evidence increasingly suggests it is, a genuine, persistent, localized, energetically extreme astrophysical object that produces no electromagnetic radiation through its own processes, then it represents something that the instruments and methods of electromagnetic astronomy are fundamentally not designed to find. Not because those instruments are inadequate in any conventional sense, because they are built on the assumption that things radiate, and this thing apparently does not. What we are detecting is not the object. We are detecting its shadow, the mark it leaves in material that surrounds it. The secondary emission produced not by the source but by the environment the source happens to inhabit. We are reading a footprint without seeing the foot. We are measuring the displacement of water without seeing the stone that fell. And when we point every instrument we have, radio, infrared, optical, X-ray, and now gamma ray with improving precision, at the place where that footprint traces back to, we find nothing. A region of space that is, by every measure our instruments know how to take, empty. There are two ways to hold that fact, and they are both honest. The first is the reassuring version. Science has been in positions like this before, where an anomaly seemed to resist explanation until a new framework arrived that made the anomaly not just explicable, but obvious in retrospect. Pulsars arrived as unexplained, unnervingly regular radio signals before rotating neutron stars were understood. Fast radio bursts were disputed, marginal detections before they became a catalogued phenomenon with physical explanations. Gravitational waves were a prediction of general relativity that many physicists doubted would ever be directly detected before LIGO heard two black holes collide in September of 2015. In each case, the anomaly preceded the understanding by years or decades, and when the understanding arrived, it expanded the field rather than breaking it. There is genuine reason to expect that something similar will happen here. Someone will find a detection method that reaches the source directly. Someone will construct a theoretical model that predicts dark accelerators and makes testable predictions about their properties. The invisible will become visible, the way it always has. The second version is harder to sit with, and it deserves the same honest attention as the first. The version where this is not just one unexplained source waiting for a clever resolution, but the first confirmed glimpse of an entire category of reality that electromagnetic astronomy cannot access. Where the Milky Way contains objects of enormous power operating in a physical regime that produces no light of any kind, and where our census of the galaxy's high-energy environment is not nearly complete in the way we assumed it was. Where the gap between what we can detect and what actually exists is not a temporary condition of technological immaturity, but a structural feature of the observational approach we have been using for 4 centuries. We have built better eyes, continuously, for hundreds of years. We extended our vision from visible light into radio waves in the early 20th century, and found a galaxy full of objects invisible to optical telescopes. We extended it into X-rays and found black holes and neutron stars and superheated plasma. We extended it into gamma rays and found the most extreme accelerators in the universe. Every new window revealed a new population. Every time we assumed the picture was nearly complete, the next window showed us how much we'd been missing. LHAASO J2108+5157 is not happening at a forgiving distance. It is not a faint signal from a galaxy billions of light years away, where ignorance is understandable and the distances themselves provide an excuse. It is happening in our own galaxy, in the same spiral structure that contains our Sun, at a distance of roughly 10,000 light years, close enough, by the scale of the Milky Way, to be considered a neighbour. Something extraordinarily powerful is operating in our cosmic backyard, and after 5 years of looking at it with every instrument humanity has built for exactly this purpose, we cannot tell you what it is. We can tell you the energy. We can tell you the direction. We can tell you it is real. We cannot tell you what is there. That might be the most important sentence in this entire story. Not because it represents failure, but because it represents the exact location of the frontier. The place where what we know ends and what we do not yet know begins. And frontiers, in science, are not dead ends. They are where the next thing happens. The question is no longer only what is hiding in the molecular clouds near LHAASO J2108+5157. The question is whether the universe contains entire categories of powerful, consequential, physically real objects that produce no light at all, and whether we are ready to build the tools and the frameworks needed to find them. We found the most powerful accelerator in the galaxy. It is invisible, and somewhere in that silence, if we are paying attention, might be the outline of the next chapter of astronomy.